All right. So there are a number of refrigeration diagrams. The first one is a generic heat pump. And when you talk about a heat pump, in principle, you can move heat either way. I can pump heat from one point to another. Now, if they share the same airspace, it really doesn't do any good. I can't have a heat pump in an open room like this because the air will undo whatever heat pumping I'm doing. But if I have two rooms, and you could think of a refrigerator as its own room, and outside of the refrigerator as a separate room, because they are separate air spaces. Now I can pump heat from point A to point B. Now, blue is represented by cool. The red is represented by hot. So what happens? I have a refrigerant, a liquid or gas, depending on the heat and pressure, that's running through the system. And red and blue just indicates where is it cool and where is it hot. And I have a pump. Number 4 here is a compressor pump. And what it does is it compresses that cold gas refrigerant and makes it hot again and makes it a liquid again. So now I've got high pressure compressed gas. And as that compressed gas goes back and forth through these like radiator tubes, and these radiator tubes are called a condenser because the gas is condensing back to a liquid, cooling back to a liquid a little bit as it gives up its heat and gives off heat to the atmosphere. So the pressure from the compressor makes the refrigerant hot. And because it's so hot, it radiates heat out into the air of the room. This is outside the refrigerator. And this is like a radiator, and it's giving off heat into the room. So if I have a refrigerator working in a room, the refrigerator is actually heating the room while it's making the stuff inside the refrigerator cold. You're not getting rid of heat magically. You're moving heat from inside the refrigerator outside the refrigerator, and it gets outside through this condenser coil, the hot side, or sometimes called the high side, high pressure side. Okay. So again, we've got hot, high pressure gas coming out of the compressor. And as it cools down a little bit, doesn't take much, cooling down, it starts to turn to a liquid, giving off even more heat. Going from gas to liquid gives off even more heat, right? It gets even hotter. But because it's going through a thin tube out in the air, maybe if you've got a really high-end refrigeration system, maybe you've got water running over this, cooling this off. But you're trying to get the heat out, away, cool this refrigerant back down. And by the time the refrigerant goes through the long winding path of this condenser, it is now 100% liquid. It's still quite warm. It's still hot, but it's lost a bit of that heat that it had here, quite a bit of that heat. It's radiated it outside the room. So the condenser is getting heat out. Then we get to number 2, the expansion valve, and it's drawn very simplistically here, but it's basically a very controlled valve that is small enough of a hole that the release of the refrigerant from the high side, the hot side, is very slow into the other side of the valve. And this is not a vacuum, but it's a much lower pressure environment, a slight vacuum. High pressure, low pressure. It goes to the low side. What happens when I release all of that pressure on that liquid? It immediately starts to boil. I've removed the pressure. Remember the syringe. Remember the lack of pressure on water allowed it to boil even when it is quite cool. And with a good refrigerant, it's going to boil very rapidly. And in the process of boiling, what does boiling do? It makes things colder. Boiling makes things colder. It's removing heat as the energy of heat goes from the lower energy state of the liquid refrigerant to the higher energy state of a gaseous refrigerant. Now, a higher energy state, in order to become a gas, it needed more energy to be a gas, and that energy is taken from the environment as heat. So now I've got really, really cold refrigerant, and it can get really cold. You can get ice buildup on the evaporator coils. They call it an evaporator coil because on this low pressure side, the low side, low pressure, low temperature, this liquid refrigerant is boiling and turning to gas very rapidly. And it can get so cold that you can really hurt yourself on this. And it goes through this series of evaporator coils. By the time it gets to the other side, it's all boiled off. There's no more liquid refrigerant. It's all gas, very cold. And in the process, this extremely cold set of coils inside the refrigerator makes the inside of the refrigerator itself cold. So any heat in the refrigerator from the warmer food items that you just put in, from your grocery shopping, whatever, you open the door, get rid of the cold air, a little warm air goes in, you shut the door, and now I've got heat inside of the refrigerator, a little bit that I let in, and that can cool down based on all of the cold refrigerant inside the coils. Now that it's cooled down inside of the refrigerator, the very cold gas refrigerant goes back into the compressor. The compressor crushes it down under high pressure, which heats it back up. You smash a gas under high pressure and it gets hot just because of the pressure you put on it. Pressure generates heat. So I generated heat. And where does that heat go? It goes into the formation of liquid, which generates even more heat. And then it has to escape somewhere. And so it goes through the condenser coils and the heat radiates out into the environment. And what have I done? I've moved heat or pumped heat from the inside of the refrigerator to the outside. In theory, this works both ways. I can heat something. I can make the inside of the refrigerator hot just by flipping this thing around. And then I'm taking heat from the outside and pumping it into the refrigerator. In theory, that works, and in practice, it actually works too, but it's not very efficient to move heat that way, to make things hot. It's a heck of a lot more efficient to make things hot just by turning on a burner, using something like a furnace that you have in your house where you take a gas burner and you heat the air and blow the air. That is much more energy efficient. Making things cold is tougher. You can't just burn something to make it cold. How do we make things cold? With a heat pump at the cost of a lot of energy. Refrigeration is extremely energy intensive, and it's one of the reasons that human civilization is so energy intensive in modern times. Nobody had refrigerators, 150 years ago. They weren't invented yet, or at least not commercial refrigerators. People were able to make blocked ice on large scale industrial level, and people could use those blocks of ice. The concept of a heat pump had been invented. I can't remember when that happened, but it's been around for a long time. But the idea that you have a refrigerator that you plug into the wall and run it by electricity in every kitchen, and a second refrigerator maybe in your garage, and your drinks refrigerator in your bedroom, that's very modern. That is something that really exploded in the post-World War II era, and largely exploded again in the prosperity of the 60s and 70s. Really ramped up in terms of people just expecting to have refrigeration in every home, and multiple refrigerators in every home. So we can use heat pumps to pump heat either direction, but because of the energy intensive nature of heat pumps, refrigeration units, we don't call them heating units because they're not really effective at that. We kind of bite the bullet and say we're willing to spend the energy on refrigeration because there's no other way to do it efficiently. But there are better solutions for heating. So this is a generic heat pump diagram. You should recognize this, and you should recognize, excuse me, the flow and how it goes. Now, this diagram without the arrows, it's really hard to know which direction does it flow. The arrows tell you, and the color tells you. But what do we have here? Let's look at this condenser coil, the hot side or the high side, as it's often called. It's often called the heat exchanger because it moves heat or exchanges heat with the outside environment. Now, if you're really needing to get something cooled off and you don't want to heat up the building with all that excess heat, you can put the condenser outside. Put it on the roof, put it on the outside, put it, if it's on the roof and it's in the sun and it's too hot on the roof, how are you going to get rid of heat when it's over a super hot roof? You can't do that. So if it's on the roof, it has to be somehow shaded, shielded, maybe using water. You can run water over the coils to cool them off. There's lots of ways to get rid of heat from this condenser, but you have to design it appropriately. And that's why sometimes refrigerators just don't work in the garage, because the garage is so dang hot. There's no insulation, especially if you're in a hot place. You're in Bakersfield, you're in Yuma, Arizona, you're someplace where it's really hot. You stick a refrigerator in the garage. It overwhelms the ability of this condenser to get rid of heat into the hot room. They work fine in the house because they're designed to work under 80 degrees. If the room's under 80, it can handle it. If it goes over 80, most refrigerators can't handle it. They're not designed to be able to get rid of heat here. And if they can't get rid of heat here, what goes past the expansion valve? Refrigerant that's too warm. And therefore, if it's already too warm, you're not going to get the cooling on the other side either. And it's going to be a very lackluster cooling on the inside. Your refrigerator isn't going to work that well. Your freezer, you're going to have slushy ice cream instead of ice cream at the proper temperature. Your milk is going to go bad too fast because it just can't keep up. And this is why your condenser has to be cool. Number two, the expansion valve. That's where you release the pressure, and now it's on a vacuum or low, mild vacuum on the other side. The gas expands. Actually, it's mostly liquid by this point. The evaporator coil, the cool side heat exchanger. So this is where you take heat out of the refrigerator. The compressor compresses again, round and round we go. Now don't worry about where is it actually a gas, where is it actually a liquid. It kind of depends on the design of the system. At what point does it turn liquid? At what point does it turn gas? Don't worry about that. Now here is a better diagram that you can look at that's more of an engineering diagram that doesn't rely on kind of the cheating cues of color. But you still need to recognize it. It's flipped over. Don't get confused. Here is a proper diagram illustration, an engineering illustration of a compressor. You notice it forms kind of a wedge shaped where the low pressure side is here where it's wider, and it compresses or squeezes that refrigerant down to high pressure at the narrow end. So you always know the direction things are flowing based on the compressor. The compressor in a proper design diagram, engineering diagram, the compressor acts as an arrow. In this case, the refrigerant is flowing clockwise. In this case, the refrigerant is flowing counterclockwise. It doesn't matter, just follow the diagram. So what happens when it's compressed? It always goes from compressed straight to condenser. Because what does compressing do? Make it hot, high pressure, the high side. Gets rid of heat to the environment. So this is hot, high pressure, getting rid of heat to the environment. It turns to a liquid as it is cooling. It is under low pressure as soon as it passes the expansion valve, which looks like this kind of an odd bow tie or figure eight, whatever you want to call it. That's a proper engineering diagram symbol for an expansion valve, and it comes out as boiling liquid refrigerant, which is a combination of liquid plus vapor, the boiling vapor, or the boiling liquid giving off vapor. But it's trapped in these tiny tubes. It's boiling, but it's trapped in these tiny tubes. And then it wiggles its way back and forth, much more than it does in this diagram. I mean, it would be, there would be just stacks of tubes like a car radiator. And that car radiator style zigzag of tubing is called the evaporator. Because what's happening? The liquid is turning to gas. And as the liquid refrigerant turns to gas, you end up getting really, really cold. As it boils, it gets colder and colder and colder. And then you have some sort of a fan. You got to blow that air around. It's not good enough in many cases. In other cases, it's fine to just have an evaporator sitting there and passively let the temperature get around the room or refrigeration unit. But most of the time, you at least have a small fan to keep air moving, to circulate it, so any warm air can come in contact with the evaporator and cool off. Any cold air next to the evaporator can go down and go past and contact the material that's in the refrigerator unit. So if I put my milk that's been in my car for an hour as I was shopping, it's not quite as cold as I would want it, so I stick it in the refrigerator. That fan is circulating the cold air around and bringing the warm air back to the evaporator to cool it, okay? This is inside the refrigerator, outside the refrigerator. By the time you get to the other side of the evaporator, it now should be 100% vapor. The refrigerant is now a cold vapor. If it's really taken on a bunch of heat. It might start to liquefy a little bit at the end. Doesn't matter. Again, I told you, don't worry about the details exactly. When is it a mixture of vapor and liquid? Kind of depends on the unit, kind of depends on the working conditions. But for the most part, I think this is one of the better diagrams to show you what is going on and what you generally would expect, what's easy to visualize and what to expect, where you would see liquid vapor and a combination of boiling material. So it gets to the end, it's already done its refrigeration work. It's picked up a little bit of heat from inside the refrigerator. And so now you compress it again. It's still cold here, but it's picked up a little bit of heat from inside the refrigerator. And then you compress it back again. And what was cold vapor is now hot vapor. And it starts to condense in some cases pretty quickly. So it might be condensing here. You might have a little vapor plus liquid right away, but certainly by the time you're giving off heat in the condenser, it's turning back to a liquid. So why don't we use water for this? Why do we use refrigerants? We use refrigerants because they're more efficient. Water is a great material to demonstrate, but water holds on to so much heat. And water can ice up at normal temperatures, temperatures we want to run the system at. It would be very difficult to make an efficient refrigeration system using water, and you really couldn't use water for the temperatures we want to keep our foods. Water just, it's a great demonstration material in a video when we're looking at boiling, and we do use water as a refrigerant in pressure chambers, which we'll get to at another time. But for an actual heat pump style refrigeration unit, we generally use things like Freon. Freon is something that's used in a lot of automobile refrigerant systems called your air conditioning unit or home air conditioning, or something like a Freon, similar to a Freon, due to environmental concerns. We've moved to alternative materials. And for large scale, non-transport types of refrigeration, we use anhydrous ammonia as the refrigerant. Anhydrous ammonia makes an excellent refrigerant, and it's a fertilizer as well. In high concentrations, it's very dangerous to breathe in, so you need it to be stable. You can't have an anhydrous ammonia air conditioner in your car, and then you get in a car accident and nobody's hurt except they all died because they inhaled anhydrous ammonia fumes. Once the anhydrous ammonia dissipates, again, it's just a fertilizer. It's not that big of a deal. Large scale ones can be an environmental problem, but it's really the concentrated material that is the biggest concern. And so you need professional commercial refrigeration units, not even at grocery stores. You do not want to have a refrigeration leak in a grocery store with anhydrous ammonia. Too dangerous for the general public to come in and people who really don't understand refrigeration working there. So it's only at large warehouses and produce cooling facilities. Let's take another